Right, so we finished last week talking about the Kirchhoff loop rule and the Kirchhoff junction rule, and that's not all there is to say about the Kirchhoff rules, but before we can get there, we actually need to have a little bit more understanding about things that are called transients, i.e. what happens in the short term, what does the current actually do as a function of time. So the first thing that we're going to talk about that involves transients are RC circuits. I don't know why it's jiggling so much. Oh, because there's a wire underneath. Oh, and now it's unplugged. There we go. Right, so we're going to talk about RC circuits. So I mentioned on Thursday that we cannot use typical parallel and series methods to quote unquote solve a circuit with both the capacitor and a resistor. I.e., it's just not possible to do. And that's because it doesn't really make sense to say that there is an equivalent capacitance for a capacitor that's in series with a resistor, because it's not just a capacitor, it's a capacitor and a resistor then. So we have to do a little bit more. And so to handle these, I mentioned that Kirchhoff's rules, or Kirchhoff's circuit laws, will be applicable to help us solve those problems. And indeed, that is what happens. So we're going to look at the simplest case first, just to get an idea as to what kind of phenomena occur. So the simplest case is just we have an initially uncharged capacitor and the capacitor is in the circuit below. So we have a battery, we have a switch, we have a resistor, and then we have a capacitor. And it's just connected like this. So initially there's no, RC stands for resistor capacitor. Sorry if that wasn't clear. Initially there's no current flowing at all because the circuit is broken. The switch is open, so there's no current flow. So the question is what happens if we flip the switch? If we close the switch, rather. So we know that, so you might think that current shouldn't flow because how does current flow through a capacitor when it's just two plates that aren't connected? But then at the same time, we do know that somehow the capacitor is going to get charged. So it might seem a little confusing. So instead what we'll do is we'll just apply Kirchhoff's loop rule. There's no junctions here, so we don't have to worry about the junction rule. So we're going to apply the loop rule. So to do so, we need to first guess a direction of current. So we're going to guess that the direction of the current is clockwise. CW, clockwise. And we're also going to traverse the loop clockwise. So we're going to go around the loop using the loop rule in a clockwise manner in the same direction as the current, just to make things easier. And then we can pick any starting place, as you guys probably have learned from doing the homework. It doesn't really matter where you start, you always end up with the same equation. So maybe we just start like at the bottom left. But it doesn't matter. So the question is so as we go around the loop, we're going to encounter a battery. We know how to handle that. We're going to encounter a resistor. We know how to handle that. And then we're going to encounter the capacitor. So the question is what do we add or subtract when we pass by a capacitor? So when passing by a capacitor, I actually mentioned this in passing on Thursday. It's basically just treated like a battery. So when you pass by a capacitor, if you're passing from the negative side to the positive side, you just add delta V cap, and vice versa. And similarly, if you guys know what I mean, but I need to write this out. Similarly, if passing from the positive side to the negative side, then we subtract delta V cap. So, and this kind of makes sense, right? If you go from the negative side to the positive side, on the negative plate, the voltage is lower than on the positive plate. So the change in voltage as you cross that, as you go from that negative to that positive, is going to be positive. So you add that delta V cap. Similar, however, if you, and by the way, delta V cap is just always defined to be, not always, but it's typically defined to be positive. So it's the absolute value of the difference. And similarly, if you are going from the positive to the negative side of the capacitor, the voltage on the positive side is higher. So as you go from positive to negative, your potential difference decreases. So you would subtract this potential difference. So that's fine if the capacitor already has charge. But the question in this case is which is the positive side of the capacitor if it initially has no charge? So if the capacitor initially has no charge, all we do is we just try to figure out where the charge would be if the current was going in the direction that we guessed. And I'll explain that in a minute. So what I mean by that is, so we guessed that the current will flow like this. We guessed that it'll go like this. So what that would mean is that positive charges, this isn't actually how it happens, it would mean that positive charges come out of the positive terminal of the battery and then go along the top and then go down. And so that would mean that you would end up with an accumulation of positive charges on the top plate of the capacitor. And similarly, you would end up with an accumulation of negative charges on the bottom plate. So if the capacitor has no charge, the way we figure out if we're going from negative to positive or positive to negative is just imagine if the current was going in the direction we think it is, which one would end up being the positively charged side if you let current flow, right? So in this case, using the guess that we've made, we would just we would subtract the voltage across the capacitor because we would be going from positive to negative. So now we're going to actually write out our equation. So imagine that the switch is closed. Imagine that the switch is closed, and note that regardless of how long we wait, the equation will still be the same. The only difference is that the voltage across the capacitor might be changing with time, and the current might be changing with time, but it's still the same equation. It just depends on time now. So we can now just write out that loop rule, regardless of how long after the switch was closed we've waited. So the first term would be, oh, let me label the battery as with an EMF. So we have plus E, because we're going from negative to positive for the battery. Then we are going in the direction of current across the resistor, so it's minus I times R. And then we are going from positive to negative for the capacitor, so it's minus delta V cap. And that's all equal to 0. So that's the loop rule for this particular circuit. So then the question is, what is delta V cap? Like, what is the actual potential difference across the capacitor in terms of variables that are useful? So remember, from the definition of capacitance, that the charge on a capacitor is equal to the capacitance times the voltage across that capacitor. And this voltage really is the potential drop across the capacitor. So this is just to say that delta V cap is Q divided by C. So we can take that and plug it in, and we end up with the formula E minus IR minus Q over C equals 0. And so this is our equation that almost completely governs the behavior of this circuit. So if you knew what the current was through the circuit, I, you could figure out what the charge is on the capacitor at that instant in time, just by plugging in, right? Because well, assuming you know what the capacitance and the resistance and the EMF are, and things like that. So this is just a warning, words of warning. You can't like change I without changing Q, right? They're related to each other by this equation. So if you increase the charge, then that means that you have to decrease the current and vice versa, because if Q goes up, That means that I has to go down to keep the whole thing equal to 0. So we're actually going to derive the explicit relationship between the current and the charge on the capacitor. By the way, remember that this is the charge separation of the capacitor. So what this is saying is that there's plus Q charge on one side and minus Q charge on the other side. Just keep that in mind. And this I is just the current across through the whole circuit. Right. So we'll derive explicitly what that relationship is between Q and I in a minute. But first, let's just do some let's try to understand the circuit from a limiting behaviors perspective. So first, we need to define a time variable because we know things are going to change with time. So let's just do that. Let's just define that t equals 0 when the switch is closed. So then we can ask what happens when t is really, really small, i.e. right after the switch is closed. We could ask, how does the circuit behave then? We could also ask, how does the circuit behave if you wait for like 10 years after the switch is closed? We can try to understand both things. So first, let's talk about the first one. So let's talk about when t is very, very small, i.e. right after you close the switch. So right after we close the switch, well, we know that the capacitor is initially uncharged. So for very, 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 very small t, we can just effectively say that the charge on the capacitor is 0. Because the switch was just closed, so it didn't have enough time to change its charge. And so, so what that implies is it implies that Q of 0, so Q is now a function of time, is just 0. The amount of charge on the capacitor right when the switch is closed, it hasn't had time to change yet. And so we can plug that into the loop equation. So the loop equation is actually an equation for all values of time. So we can plug in the charge as a function of time, and we'll get the current as a function of time, for example. So let's do that. We have that the EMF doesn't change. It's just whatever the EMF is of the battery, minus I of 0, because it depends on time, times R, minus Q of 0 divided by C equals 0. Now Q of 0 is just 0. That's what it means for the capacitor to be uncharged. So what this implies is it implies that the current at time 0, right when the switch is closed, is just equal to E divided by R. And so this is exactly what you would expect if the capacitor was absent. So the moment the switch is closed, right after you close the switch, the circuit behaves as if the capacitor wasn't even there, as if it was just a wire. Like if you had just replaced the capacitor with an equipotential, it behaves exactly like that. So in other words, an empty capacitor behaves like an equipotential. And this is not special to the circuit I just drew. This is just true about capacitors. If the capacitor is empty, it behaves exactly like an equipotential might. Sorry, it behaves like an equipotential until it fills up. So all we established is that when there's no charge on the capacitor, the circuit behaves as if that capacitor wasn't there. But the moment there's charge on the capacitor, that's just not true anymore. This calculation we just did just doesn't hold. Now, in the limit where we wait a really, really long time, we can also try to understand what happens. So a long time after the switch is closed, the potential difference, so we know that when the switch is closed, current will start, or we guessed, current will start flowing around in a clockwise manner. And so what that means is you'll be adding more and more positive charges to the capacitor, and you'll be adding more and more negative or more and more positive charges to the top plate and more negative charges to the bottom plate. And so eventually there will be so much positive charge on the top plate, so much negative charge on the bottom plate that the charges aren't attracted to one of those plates. So at that point, the capacitor is said to be fully charged, meaning it like in the circuit as given, it can't gain more charge, i.e. there is no potential difference between one side of the plate and the other and the battery, and so there's just nothing drawing the charges from one side to the other. This is all just to say that the voltage difference across the capacitor will have grown so much that the charges can't stick to the plates, i.e. think that you have a whole bunch of positive charges on one of the plates. If you have so many positive charges, you would need more energy than is available to take another positive charge and add it to that plate, because those positive charges repel each other. And so, so this occurs if you wait sufficiently long. And so obviously waiting infinitely long would be sufficiently long. So at this point, when t goes to infinity, we say that the capacitor is fully charged. That's what it means to be fully charged. So in particular, the amount a capacitor can be fully charged actually depends on the circuit that it's in. So if you increased the EMF, the capacitor can fully charge to a higher potential, to a higher total amount of charge, because the EMF has more energy to push charges onto the plates. So fully charged is respective to the circuit in particular. So we'll actually see what happens. We will do that explicitly. So, so at this point, we say the capacitor is fully charged, and we see that delta V cap is equal to the EMF. So that kind of makes sense, right? So if the voltage drop across the capacitor is equal to the voltage drop of the EMF, there's no reason for charge to go from one plate to the other, because that would just throw off the balance, and then you'd have charge flowing the other way. So when this happens, when the capacitor is fully charged, that means that the capacitor has equal charge, has potential difference that's equal to the EMF in the circuit. So what this implies, this implies that delta V cap as t goes to infinity is equal to EMF. So we can plug this in to our loop equation. We're not plugging in Q anymore. We're just plugging in Q over C, which is equal to delta V cap. We have EMF minus IR, and then we subtract off, and that's I as t goes to infinity times R minus delta V cap, which is just E, equals 0. And so what that implies is that the current as time goes to infinity goes to 0. So just like how an empty capacitor just behaves like an equipotential, i.e. just a wire, until it fills up, we have that a fully charged capacitor behaves like an open switch, i.e. no current can pass through it. And that is until it's discharged. So those are the two limiting behaviors of capacitors. And if you ever need to think about like just get an idea as to what happens for a capacitor in a circuit that's not fully charged or not fully empty, it's just somewhere in the middle. So initially, it behaves like just a wire. Current can just flow right through it. But but as time progresses, the current flows through it slower and slower until there's no current flowing through it at all, at which point the capacitor is fully charged, and that takes approximately an infinite amount of time. The word for this, by the way, an open switch, there's another phrase for that, and that would be called an open circuit, just like how an equipotential would be called a short circuit. A short circuit means that there is a direct connection between 2 points. So in particular, if we replaced this capacitor with just an equipotential, there would be a short circuit where the capacitor is. It's shorted. Short circuits are usually bad because it means that you have a lot more current flow than what you typically want. But because capacitors in a charging setting like this are only very temporarily behaving like short circuits, it's usually not dangerous. An open circuit, on the other hand, is usually not dangerous at all either, because there's no current flow, so there's no risk of anything getting damaged. but also it can be another means that or it can be another way that something breaks. If the circuit goes open, it means that that an equipotential broke somewhere, which means that you can't be doing, or whatever device you're operating can't operate because there's no current. So that was just a little bit of an aside. So, okay, that tells us about what happens when the current, or that tells us what happens to the current flowing through the circuit at right when the switch is closed, and if you wait like an infinitely long time after the switch is closed. But what about in between? What about for all the times the instant after you close the circuit, after you close the switch, but not after you've waited an infant, like 5 seconds after you close the switch? What happens there? So now we have to do a little bit more work. So before we actually study the example that I just gave, this is a charging circuit because the capacitor is initially uncharged, then we close the switch and it becomes charged. We need to actually understand a simpler circuit first. So let's talk about the discharging capacitor. So capacitors basically have two functions, right? They can either charge and store energy, or they can discharge and release energy. So we're going to talk about the discharging case first, just because it's easier from a mathematical perspective. So let's suppose that we have a charged capacitor. And in the circuit that I'm about to draw. So we have some capacitor with, say, minus charges on the left and positive charges on the right. And it's hooked up in the circuit here. So here we literally just have a capacitor and a resistor. And so you'll see that if we close the switch, the capacitor almost behaves like a battery, right? You have a potential difference, and so that potential difference causes a current to flow through the resistor. And so you'll have positive charges that race around, pass through the resistor, lose some energy, and then end up at the negative side. And so what happens is the capacitor ends up discharging because you have positive charges moving through the resistor to cancel out with the negative charges. And so the overall charge on the capacitor, the charge separation, decreases. So just for the sake of calculations, let's assume that the capacitor initially has charge separation Q naught. Q naught. And let's say that the switch is closed at t equals 0. So what that implies is it implies that the charge on the capacitor at time 0 is just equal to Q naught, hence the name, right? So the question is, how do we solve this circuit? So when we talk about solving a circuit, typically what we mean is we want to know the current through every element. We want to know the voltage across every element. And for capacitors, we want to know the charge across that element, or the charge separated by that capacitor. And for circuits like this, where it's changing with time, we want to know all of those things at every instant in time. And so what we have to do is we actually have to solve not for a number, but we have to solve for a function. Say the charge as a function of time, the current as a function of time, and so on. So that's what we're going to do. So fortunately, we can still apply the Kirchhoff's loop rule here. And that's just because even though these variables, Q and I and so on, are changing with time, they still always, at any given instant in time, they still have to obey the Kirchhoff rules. So we're going to, there's no junction here again. So we're going to just use a single loop. We're going to guess a clockwise current, and we're going to use a clockwise loop. Again, we could have done any of them, or any configuration. We could have guessed counterclockwise current. We could have used a counterclockwise loop, or any combination of those, but this is just the easiest example. So let's say that we start in the top left. So first we cross a capacitor from negative to positive, which means we add delta V cap. Now delta V cap, we have a formula for, right? It's just equal to Q over C. So the first term is Q, and I'm going to write these things as functions of time because they are. First term is Q of t divided by the capacitance. That's the term for the capacitor. Then we go along and we pass by the resistor. Now, we're assuming that the current goes this way. So that would mean that when we cross the resistor, we subtract the current times the resistance. And again, the current is also changing with time. So that's I of t times R. And that's all we have. That's just equal to 0. And so we can rearrange this, and we get that I of t is equal to 1 divided by RC times Q of t. So already this is a good start. We always assume that the current and loop are in the same direction. Not necessarily. If you have junctions where you have multiple different currents, they're not always going to be in the same direction. It's just in the simplest cases, sometimes it's easy. But this is not an assumption that we're making. This is just a guess. And if it turns out that our current is negative, then we just made the wrong guess. That's all. Right. So this gives us a relationship between the current and the charge. But just like any equation, if you want to solve for, if you have two unknowns and you only have one equation, you can't solve. You need another equation to solve for those unknowns. So basically, we need another equation that relates the current to the charge. And it has to relate those things at all points in time so that we can then use those two equations to solve for I of t and Q of t. And by the way, once you know I of t and Q of t, it's really easy to get the voltage across any particular element just by either using the relationship between charge and capacitance or the relationship between current and resistance. Right, so we have to think a little bit physically here. So we need to think about what current is and how that relates to the charge on the capacitor. So just as a quick, not as a quick note, this is actually important. So the current in the circuit is just the rate at which charge flows through the circuit, right? It is the rate of charge flow. That's all current is, right? It's dq dt, but not explicit, not let's like d little q dt. It's the rate of charge flow in the circuit. In this particular circuit, that charge comes from somewhere. And it comes from the capacitor. So any current that flows through any, like say you have a single electron. So when it is discharging capacitor, Q naught is not initially 0. So we never use Q naught to mean 0. We always mean Q naught to mean just some number. 0 is 0. We would write 0 if it was 0. Notice how I didn't use Q naught. I just used Q of 0. Right. So that charge comes from the capacitor. So for every electron that flows around the circuit, that means the capacitor is losing an electron. So if we imagine that the current is positive in the direction that we've guessed, that would mean that you have a positive charge. If you have one positive charge leaving per second, say, that would give you a certain current. It would be, 1.6 times 10 to the minus 19th coulombs per second, which is a current. And that would also tell us the rate at which the charge on the capacitor decreases. And so because the charge is decreasing, because the rate at which the charge is decreasing on the capacitor is equal to the rate at which charges flow around the circuit, and hence is equal to the current, we have the following relationship. We get that the current, say as a function of t, is equal to the negative time derivative of the charge. This kind of makes sense, right? Or at least hopefully it does intuitively. The amount of charge on the capacitor just tells you how many electrons, how many spare electrons the capacitor has. For every one electron that leaves, the rate at which the electrons leave tells you two things. One, it tells you how much current is flowing through the circuit, because if you have an electron leaving the capacitor, it has to go through the whole circuit to get back to the other end. But it also tells you that an electron left, which tells you that how much the total charge on the capacitor decreased by, which is why we get this relationship here. Notice that this relationship is only true for a discharging capacitor. And so whenever you're handling a more complicated example than the one that I just gave, like if you have a whole bunch of resistors and a whole bunch of capacitors and so on, you have to consider what what charge, maybe the charges are labeled Q1, Q2, Q3 for capacitors 1, 2, and 3, for example. Which charges are related to which currents, and how do they relate to each other? If one of the currents is positive, does that mean that the rate of change of the decrease of charge on the rate of change of on the capacitor is negative, and so on. So this negative sign accounts for the fact that the charge is decreasing on the capacitor. So if we were to plot Q of t is going down, so the slope is negative. So by sticking a negative sign in front, we're making the whole thing positive, which is why, or which it has to be, because current is defined to be positive if our guess is correct. If our guess of the current for the current direction is correct. That's where this relationship comes from. So this is all to say, don't just blindly apply this equation, because it's not always true. It's only true for the particular scenario. You have to come up with the similar and equivalent relationships for whatever circuit you're working with. And we'll do this again later today. But anyway, we now have two equations. One equation, two equations. They both relate the charge to the current. So we can combine these equations. I'm just going to substitute I. We get that minus dq dt. Yeah, basically. But you have to, and there will be similar equations for different circuits, but you will have to figure out what that equation is. Which current relates to which charge and in what way? Is it positive? Is it negative? Whatever. Right. So I'm just plugging in this here. So negative dq dt is equal to 1 over RC times Q of t. Excellent. Okay. So now this is an equation with one variable. In this case, it's a function. The function is Q of t. And now we need to try to solve it. Fortunately, hopefully you guys have seen this sort of thing. This would be what's called a first order, because it only has one derivative. Linear, because it doesn't have squares of Q or cubes of Q or square roots of Q or sines of Q or whatever. First order, linear, and it's a differential equation because it has a derivative. And so this is an equation. Yeah, exactly. This is a crossover episode. They told you that it would be useful. Physics is literally just differential equations applied to the real world. Right. So this is a first order linear homogeneous differential equation, right? Because there's no non-homogeneous term. So now we just have to solve it. And the easiest way to solve it is you just separate variables. So what we're going to do is we're going to separate variables. So this equation is equivalent to the equation dq over q, and the math department might hate me for this, is equal to minus 1 over RC times dt. All I did was I multiplied both sides by dt and divided both sides by q. Okay, and then I'm just going to integrate. Now, you'll often see this done in a different way. Like in the textbook, it's done in a different way, how they do this integral. I'm going to do it as a definite integral. So if we want to know q as a function of t, that means that we need to, and we only know one value, yeah, and we only know one place where, if we only know the value of q at one place, say at t equals 0, then that means that we ought to integrate from 0 to the variable t. So t is just some variable, we're integrating to that variable. So on the left-hand side, our variable is q. So the thing we integrate from is from q of 0 to q of t. And we integrate dq over q. On the right-hand side, we have to do the same integral, but it's with a different set of variables. So q of t in terms of the variable q corresponds to t in terms of the variable t. Q of 0 in terms of the variable q corresponds to 0 in terms of the variable t. So this would be equal to negative the integral from 0 to t of 1 over RC times dt. So now this is just a definite integral that we can do both sides, right? And you might get mad, like maybe I should put a prime there. Technically, that's probably correct, but I'm not going to, because what is this, a math class? Basically, yeah, it is. Anyway, so we can do the left-hand side. This is it's just the integral of dx over x with some bounds. So it's just the log of q of t minus the log of q of 0, right? And those are they just are whatever they are. And the right-hand side is just, well, it's just a constant times dt. So it's just minus t divided by RC. Easy integral on both sides. Then we can do some log rules, so we can combine the two logs into a log of a rational function. So we get that this is log of q of t divided by q of 0, which is equal to minus t over RC. And then you guys have seen this trick by now. You just exponentiate both sides, multiply both sides by q naught, and so you're left with q of t is equal to q of 0 times e to the minus t divided by RC. And we gave a name for q of 0. We just called that q naught. So really what we have is we have that q of t is q naught times e to the minus t over RC. And so this is our formula, or our equation, for the amount of charge on the capacitor as a function of time. R and C are just constants, they're just given. So this tells us how much charge at any particular time there is on the capacitor in this simple circuit. Now, if you look at the formula for this, it has a particular shape, particular type. This would be known as exponential decay. So the amount of charge on the capacitor decays exponentially. So it starts off at some value and it decreases pretty quickly, but then it slows down as it decreases and slows down forever, and it never actually reaches 0. So anytime you have any sort of exponential growth, exponential decay or exponential growth rather, the rate at which that decay or growth takes place is governed by some particular constant. So in this case, the rate of decay is governed by the RC time constant. Let me put this on a separate line. The RC time constant. Of the circuit. So each circuit has its own RC time constant. Those are coming way later, near the end of the course. And so this RC time constant is often designated by the Greek letter tau, which is like a curly t that's small. So if we were to plot this function, or the charge as a function of time, it would look something like this, where here we have q naught, and this function here is q naught times e to the minus t divided by tau, where tau is RC. So that is the time constant. So the fact that it's called an RC circuit kind of gives away, or rather the fact that RC is the governing factor of this type of circuit kind of gives away why it's called an RC circuit, right? Multiply R and C and you get good stuff back. So just as a quick aside, you might ask the question, how long does it take the capacitor to reduce its charge by a factor of 2? So that would be known as its half-life. The half-life, which is some amount of time, sometimes called t sub 1/2, is the amount of time it takes for the charge to half drain. So initially you have some amount of charge. How long does it take for half of that charge to have gone away? And so we can just solve for that explicitly. So we want to solve for t sub 1/2, and the governing equation is that should be equal to the initial charge divided by 2. And so we can just do this equation. We get that q naught e to the minus t 1/2 divided by tau is equal to q naught over 2. And so we can just solve for t 1/2, for the half-life, and that's just equal to tau times log 2. So the RC constant isn't actually the half-life. It's related to the half-life by the logarithm of 2, but it's not equal to it. So if you want to find the half-life, just multiply tau by log 2 and you're done. Right, so we got q of t, right? Like we derived it using the equations and using physics. So so that tells us how much charge is on the capacitor at any given instant in time. What about the amount of current that's flowing through the circuit at any given instant in time? Well, that's relatively easy once we have Q. And the reason it's relatively easy is because we have an equation that tells us what the current is. It's equal to 1 divided by RC times the charge, right? So all we have to do is we just plug in. So that gives us that the current as a function of time is Q naught divided by RC times e to the minus t over tau. Actually, I'm going to put t over RC just for consistency. Great. So this is technically fine, but it's useful to write this in a slightly different way. So first, let's talk about what the current should be initially. So you could just look at this equation and see that's Q naught divided by RC. But we could probably do it, we could get a different formula and then relate the initial current to that expression, Q naught divided by RC. So we already know that at t equals 0, the potential across the capacitor is just equal to the total charge, sorry, the initial charge divided by C. And so if that's the potential, we can figure out how the current as a function of time relates to the, or we can figure out how the initial current, say I naught, relates to the, how do I want to phrase this? No, so it would be nice to have a name I naught for the initial current, but we need to make sure that I naught, the initial current, really is equal to this thing. And so we can just double check by just applying Ohm's law. If we apply Ohm's law here at t equals 0, then that means that the voltage, which is equal to IR, so that would mean that I at 0 should be equal to delta V cap over RC. Sorry, over R, which is just equal to Q naught over RC. And so it makes sense to call this variable I naught, it makes sense to call it, to use that as a name for Q naught over RC, because it is just the initial current. So really what we have is we have that I of t is equal to, sorry, not Q naught, it's equal to I naught times e to the minus t over RC. And again, this is just exponential decay, and it has the exact same shape. It just starts at I naught instead of Q naught, and it has different units. All right, so before we continue to the charging circuit, we have one more thing to consider. So we can also consider the energy dissipation. So we know that capacitors store energy. So if the capacitor has some initial energy, let me just give this a heading. We know that the capacitor has some initial energy, and we know that that energy is leaving the capacitor. And the only place it could go would be through the resistor and then dissipate as thermal energy in the resistor, right? Resistors, when they absorb energy and they convert it to thermal energy. So the energy in the capacitor is being converted to thermal energy in the resistor. So those two things should be equal. The rate at which energy leaves the capacitor should be equal to the rate at which thermal energy or electrical energy is converted to thermal energy in the resistor. So let's just check that that's true. So the energy leaving the capacitor, or the rate of the energy leaving the capacitor, can be found by just taking the time derivative of the energy in the capacitor. So this is the time derivative. And what's the formula for the energy in the capacitor? It's 1/2 Q squared over C. In this case, Q depends on time. So this is using the chain rule. This is 1 over C times Q of t times dq dt. Okay, so we know what Q of t is. And so we know how to take a derivative. And so after doing that, you end up with minus Q naught squared over C e to the minus 2t over tau. That is the rate at which energy leaves the capacitor. That's a Q naught squared. So then we can also ask, how much energy is dissipated by the resistors, say, per second, i.e. what's the rate of, or what is the power just power dissipated by the resistor. And we have a formula for that too, which comes from a completely separate place. So you might think that maybe it wouldn't be related to this equation. Maybe it wouldn't be equal to this thing here, but it turns out that it will be. So the formula for the power dissipated by a resistor is I squared times R. That's one of the formulas anyway. And we know what I is. We have a formula up here. And we know what I naught is. I naught is Q naught over RC. And so we can just plug this in. This is Q naught squared over RC squared times the resistance times e to the minus 2t over tau, which is just equal to Q naught squared over C hold on, something went wrong. So yeah. So we should end up with the same thing, and I'm just trying to figure out what went wrong here. Charge divided by capacitance. Oh, this is wrong up top. I just did, let me go slow and let me actually do derivatives correctly. So what we have is we have Q, which is Q naught times e to the minus t over tau. Yeah, I did do the derivative wrong. I'll have to fix that in my notes. So this is Q naught over C, e to the minus t over tau, times, and then the derivative, right? So the derivative would be minus 1 over tau times the original function, right? So this would be times Q naught, or times minus Q naught over tau, e to the minus t over tau. All right, let me move this down. So we have Q naught squared divided by RC squared. There we go, that's better, with a minus sign and then an e to the minus 2t over tau. Right. Okay, so now we find, unsurprisingly, that it does check out. We get an RC squared in the denominator because one of the R's cancels with the R outside, times e to the minus 2t over tau. Notice that these are equal and opposite. They're the same magnitude, but they're different in sign. And that makes sense because for energy conservation, we should have that the total energy entering the system plus the total energy leaving the system should be 0. And so if we just add these two things together, we would get 0. And that's precisely what we would expect from energy conservation. So I'm just going to write a note for myself to fix this. Where's my pen? Fix this in my lecture notes. So that way then I don't lie to you before I post it. Right. Okay. All right. So that's all there is to say about charge. I mean, that's not everything to say about charging or discharging capacitors, but that's the basic gist. Now let's talk about charging capacitors. And by the way, if you had like, say, 2 capacitors that were both charged and they were in series or something, or in parallel, you would just first find the equivalent capacitance, figure out how much charge it has, what its potential, or how much charge the equivalent capacitor has, solve this problem, and then you would work backwards to figure out how the charge on each of those capacitors change. Right. So charging a capacitor is very similar to what we just did. There's just one extra part that's added. So we're going to assume that the capacitor is initially empty. And it is in the circuit that I'm about to draw. So we have our EMF, we need something to charge it. We have our capacitor, which is initially empty, say capacitance C. We have our resistor, say R, and then we have a switch. right? So initially there's no charge. When we close the switch, there should be charge. This is basically the same circuit that we drew way up at the top, right? Way up here. I just switched the order of the capacitor and the resistor, but that doesn't change the equation at all. And so the question is what happens? So we're going to apply the loop rule here, as we did before. We're going to guess that the current goes clockwise. Hint, hint, it does. We're going to use a clockwise loop. And so we can just figure out what the loop equation is. So first we pass by the battery. Oh, this should have EMF E. And then we have to figure out whether we're passing from positive to negative or negative to positive for this capacitor. So if the current really did flow out the top and went into the capacitor, we would end up with positive charges on this plate, right? So the positive charges, so we're really going from positive to negative side of the capacitor. So we're going to subtract off the voltage on the capacitor, which is Q of T, remember the charge changes with time, divided by C. All right, and then we pass by the resistor, which has current passing through it, I, but that changes with time. So it's I of T times R, and this is equal to 0. So this is our equation. Again, very similar to what we have up here. There's just one extra term. Where is it? Somewhere. Here. There's just one extra term, the EMF, and that throws a little bit of a wrench into things, but it's not that much harder to solve. Yes, this is non-homogeneous, but it's an easy non-homogeneous equation. Right. So now we have to ask, how does so just like in the previous case, where we had the current that was leaving the capacitor was the charge that was leaving the capacitor caused the current. Here, we have that the amount of charge that enters the capacitor has to be equal to the current flow. Because if you have, say, 1 positive charge per second that flows through the circuit, that means that you're accumulating 1 positive charge per second on each plate, or on the positive plate. So here, in this case, we have that the current is equal to the derivative of the charge, not equal to the negative derivative, because the charge is increasing and the current is causing that charge to increase. The whole non-homogeneous equation bit, it's completely unrelated to what we're talking about. It's a math term. It just means that there's a term that's not proportional to the function or its derivatives. So you'll see what I mean in a minute. Right, so we can substitute this in. And we get the following equation. E minus Q of T divided by C minus dQ dt times R equals 0. So when we say it's non-homogeneous, it just means that so this term is proportional to the function Q. This term is proportional to the derivative of the function Q, but this term isn't. So there's a term that's not proportional to the function at all, and so hence it's non-homogeneous. And so there are different ways, different mathematical ways to treat non-homogeneous differential equations, but this is sufficiently simple that we can treat it the same way. So we're subtracting IT here because we're going past the resistor in the direction of current flow. And the reason why the current is equal to the change in the charge on the capacitor is because the capacitor is increasing the amount of charge at the exact same rate that the current is flowing through it. For every 1 positive charge that goes around the loop, you gain 1 positive charge on your capacitor. Right, so now we're going to solve this basically the same way, but we have a little bit of massaging to do first. So we get that dq, all I'm going to do is rearrange this equation. This is equal to E over R minus Q of T over RC. And then we can simplify it a little bit more. dq dt, or rearrange a little bit more anyway, is equal to 1 over RC times EC minus Q over T. And now we just divide both sides by this stuff to separate variables. And then we multiply both sides by dt. So what we get is we get that dq divided by q minus EC is equal to negative 1 over RC dt. And now we're just going to integrate again. We're integrating from Q of 0 to Q of T. on the q side, and we're integrating from 0 to t on the t side. So we have q of 0 and q of t. This is equal to, and we're integrating dq over q minus ec. This is equal to an integral from 0 to t, negative 1 over rc dt. So it's a lot like the same, we just have this extra term down here. And we have an extra minus sign. Well, anyway. And so then we just do the integrals. Now we can just do a q substitution here, I guess it wouldn't be a q substitution. We can just do this integral though, it's just a log. So what we have is on the left-hand side, it's the logarithm of q of t minus ec divided by q of 0 minus ec. All I've done is I've combined the two logs into the quotient of the two terms, standard log rule tricks, is equal to minus t over rc. And now just reminder that the initial charge on the capacitor is 0. So I'm just going to rearrange I'm going to plug that in and rearrange the logarithm a little bit. So we're left with the log of ec minus q of t divided by ec. That's equal to minus t over rc. Sorry, my nose is very itchy. And then we can exponentiate both sides and rearrange. And so we get that ec minus q of t is equal to ec times e to the minus t over rc. Or, put another way, that q of t is equal to ec times 1 minus e to the minus t over rc. So that is the current, or that is the charge on the capacitor as a function of time in the charging case. Why is the bottom term not negative? It is, I just flipped the order of the top terms. It was q of t minus ec, yeah, that's all. Right, and so we can plot this. And so if we were to plot this, we have t, then we would have, just put a dotted line here for CE, or EC rather. I like EC more. And so we get a function that looks like this. Still technically exponential decay, just inverted. And so here we have, so again, tau is the time constant. Yep, tau is just RC. And so what we have is we have Q of t is equal to CE times 1 minus e to the minus t over tau. I can't really scroll up because we have to continue. The show must go on, as it were. But I can while I talk. So if you wanted to find the current, we have a relationship with the current as exactly as we saw before, right up here. The current is just the time derivative of Q. And so you'll find that the only difference, or you'll find that the current is the exact same in both cases. And that's just because the derivative here, the derivative of constant goes away. And the relationship between current and charge in the discharging case had a built-in negative, whereas here we don't have a built-in negative, but our function has a built-in negative. So the currents are literally just the same plot. They start out high and then they decrease with time. That's a t, sorry. Tau is a constant. So that is just to say that I of t is the same for charging and discharging circuits. Do note though that the current goes in different directions in both cases. So then you can ask, what about energy usage? So we talked about power dissipation in the case of a discharging capacitor, but we know that the battery is a source of energy. So how much of the energy gets stored? So over the entire duration of the charging process? Oh, and by the way, this answers the question: how long does it take to charge a capacitor? It takes an infinite amount of time to charge a capacitor. It gets exponentially close, but it never quite gets there. Hence why we had to take the limit as t goes to infinity. Right, but if we waited a long enough time, some of the energy that had been given to the circuit by the battery was stored in the capacitor. Some of that energy would have been dissipated. So the question is, how much of that energy was stored of the total energy that was given by the battery, and how much was dissipated? So we can actually just do that calculation. So let's figure that out. So how much energy was given by the battery. So the power in the battery, just by definition, this is the power through anything, just the voltage times the current, or at least it's the power by a battery. This is something we've talked about before. And so the current, we already know the formula for the current. It's just E times, or the current is I naught times e to the minus t over RC, right? So to find the total energy output, we just note that the power is the time derivative of work, and work is the negative of the potential energy. That's from like 9a. So the change in the potential energy, stored in the battery is negative the integral of the power. So E I naught times an integral from 0, and we want to add up all of the power that was, or all of the power for a full infinite amount of time after the switch is closed. So we have to integrate that power over the entire duration for infinity. So it's minus E times I naught times the integral from 0 to infinity of this term, right? E to the minus t over RC dt. And so we can just do this calculation. This is just E I naught times RC times E to the minus t over RC, evaluated from 0 to infinity. So this is just minus E I naught RC. Okay, so that is the total amount of power or total amount of energy that's given up by the battery. Notice that it's negative, and that's because the energy is leaving the battery. Now, just as an aside, when t equals 0, the EMF of the battery is equal to the current times the resistance, because the capacitor, being that it's empty, behaves like an equipotential. So it just obeys Ohm's law. Or written a different way, I naught is equal to E over R. And so we can rewrite the change in potential of the battery as minus. So I'm just replacing I naught with E over R. So it's minus CE squared. So the battery loses an amount of energy equal to its EMF squared times the capacitance. Okay, so how much energy is stored in the capacitor? Well, that's actually really easy to calculate. We have a formula for the amount of energy stored in the capacitor. We have 3 formulas, actually. So when the capacitor is fully charged, we know that the potential difference across that capacitor is just equal to the EMF. So the energy stored in that capacitor, one of the formulas was 1/2 CV squared. In this case, V is the EMF value, so it's 1/2 C E squared. And that's precisely equal to half of the change of energy in the battery. Which is just to say, regardless of what your resistance is, what your capacitance is, if you have a simple charging circuit like the one that we've described, exactly half of the energy that comes from the battery is going to be stored in the capacitor. The other half is lost, and there's nothing you can do about that. And that it's lost by dissipation in the resistor. So the resistor will heat up a little bit and convert that electrical energy into thermal energy, and you can't really get that back. Now, at the bottom of the lecture notes, there are a whole bunch. There's a few examples. I linked to. I mentioned the 2 examples in the textbook, the Liber text. That's example 3.5.1 and 3.5.2. In section 3.5, those are pretty good examples for this sort of thing. Yeah, 50% efficiency is kind of cringe. I also linked to the Young and Friedman book. I gave a link. It's example 10.8 and 10.9. I couldn't find a link for those because of the way the website is coded. It's just awful. But regardless, those examples are also, they're a lot more involved than the kind of examples that you see in the Liber text, but I suggest you take a look at them because they're They're pretty good. And they'll make you think. So take a look at those. We do still have 10 minutes. So instead of finishing early, I just want to get a jump start on the next topic. So that's all I'm going to say about RC circuits. They charge, they discharge, and that's about it. And you can arrange them to charge and discharge like in particular ways, and you can put a whole bunch of capacitors in one place, a whole bunch of resistors elsewhere, and switches and stuff like that. But at the end of the day, it's just a matter of instead of treating current and charge as constants, now you just treat them as independent variables, and just treat the current and charge as independent variables. And then you just do the loop equations like you typically would, and then you might have some equations, some differential equations to solve at the end of the day. But all of the tools for that is laid out here. And by the way, you can look forward to one of the homework assignments is going to be some involved, annoyingly long system of capacitors charging and discharging, and there's going to be a bunch of resistors, and it's going to ask you to just solve the circuit. It's going to take you a long time. So once you see it, once I assign it on Thursday, get started on it ASAP, because it'll be a long problem. It sounds awful, but you need practice, and better do one challenging example rather than 50 tiny examples. Yeah, so typically, Mason, that the energy the energy stored in the capacitor is half of the energy given up by the battery. That's true for a simple charging circuit, or a simple charging circuit like this. I can't imagine, I'm trying to think of other ways that you could charge more efficiently, but at the end of the day, they're going to have some sort of resistor. Yeah, I think that that's probably an upper limit. You could probably charge less efficiently, but probably can't charge more efficiently than that. Anyway, right, so as someone correctly guessed, we're going to move on to magnetism, and we're just going to get a little taste of it today. So this is section 4. Magnetism is the worst, by the way. Like, it's actually the worst. I'm sorry. This is my least favorite part of the class. It's like fascinating, but it's just the calculations are really, really messy. Right, so we can talk about how they work after lecture if you want. So we're going to approach this from a slightly separate perspective than the way we approached Coulomb's law. So for Coulomb's law, we just said, look, if you have two charges, it seems that they attract. And then we just started describing that force. And eventually, we came to the conclusion that it would be really nice and easy if we instead talked about each charge producing an electric field, and then that electric field kind of communicates that force to the other charges. So we're going to do something really similar here. We're going to talk about a magnetic field that handles the force. But before we can do that, let's just talk about what actually happens. So you guys have all experienced like fridge magnets, but that's not what we're talking about here, because it turns out those are harder to explain than the kind of magnetism we're going to talk about. So if you take two long wires, just hook one up on the left, one up on the right, and you just run current through both of them, and maybe they complete a circuit elsewhere. You just run current through each of the wires. They're not touching each other. You just have current running through one, current running through the other. It turns out those two wires will either bend towards each other, i.e. there will be some force trying to pull them together, or they will bend away from each other. There's some sort of force that tries to push them apart. And if you were to try to probe this and understand this better, well, your first guess might be, oh, well, current means that there's charge. And so if there's charge, then it's just Coulomb's law, right? There's just charges that are attracting or repelling each other. But that can't be the case, because at any given instant in time, the charge in the wire it's just neutrally charged. It has no net charge, because every time you have an electron that enters the bottom of one of the wires, an electron also leaves the top. So it's not like either wire has any net charge to attract or repel each other. It also isn't a property of just pieces of metal, right? Because if you just take two pieces of wire and put them next to each other without any current flowing through them, there's no force that's exerted between the two wires. They just sit there happily. So you need to have current flowing through both of the wires in order for there to be a force. If it's just flowing through one of the wires, you get no force. And so the implication then is that it has to be related to some sort of current. Now we know that current is related to the motion of charges, so you might guess, and you could test this again experimentally, you could test this result. So let's say instead of having 2 wires, you just have 1 wire with current flowing through it, and then you just stick a charge next to it, just a free floating charge. If that charge isn't moving, then it won't feel a force. It will only feel a force if the charge actually is in motion. So the end result of this sort of experimental thought experiment, I guess that's just called an experiment. If you were to do this in real life, of course, I'm telling you this so you don't have to do it yourself, but you could go home and do these easy experiments to run. Actually, I might suggest that you do that. Get a 9-volt battery. No, bad example. Get 2 9-volt batteries. Put like a loop of, I just thought of this off the top of my head, but no, that would probably, well, it might be fine. So get a 9-volt battery, 2 of them, and then put a long wire and then make it go like this, and then just connect it back over here somehow. You're shorting a battery, but it's just a battery. It's just a single 9-volt battery. It'll kill the batteries, but whatever. And then take another 9-volt battery, take a long wire, doesn't matter how it's oriented, and then do the same. Have one of them go straight up and the other one just connects back however which way. Bring them close to each other, and you'll see that those wires either move closer or move away from each other, depending on what polarity you stuck those wires on. That it's actually something that you can observe and test in real life. 9 volts are not going to blow up because they're they have a very, very high internal resistance, because it turns out they're made of 6 teensy quadruple A batteries. And it'll be fine. Like, you shouldn't let it go forever because it'll kill the batteries, but it's not going to burn anything. Anyway, yeah, don't use steel wool. The steel wool will light on fire. Anyway, but this is something you can try at home. And you can observe these experimental facts. Right. So the end result is that from all of this experimentation is that the only way that you could get this force is if there's moving charges. So if you have one set of moving charges called current and another set of moving charges, the motion of those charges is what causes there to be a force between those charges. So if you have one charge that's moving in one direction, another charge moving in another direction, there will be an electrical force, but there will be an additional force because the charges are moving. So magnetism is really the result of charges in motion, whereas electrostatics is quite obviously the result of charges that are stationary. So like I mentioned, the way that we're going to proceed, and we will talk about this in more detail on Thursday, the way that we're going to proceed, or the way that we could proceed, is we could first try to figure out what the force is between 2 moving charges, say, or 2 wires, and then try to derive from that a sort of field that communicates that force from one wire to the other. But we're not going to do that. It's a little bit harder, and you guys are already familiar with this idea of magnetic fields. You guys know that the Earth has a magnetic field. You know that magnets have magnetic fields. So you can imagine, even if you don't understand how you got it, you can imagine that you can make a magnetic field just by sticking a permanent magnet somewhere. So what we're going to do is we're going to assume that magnetic fields exist and that they produce that they exist, and we're going to try to figure out how they affect the forces, or how they affect the forces on charged things. And then later we will figure out how moving charges produce that field. So we're going to kind of do it backwards, but it's just because it's easy to actually make a magnetic field. Just take 2 permanent magnets and put them next to each other. Then there's a magnetic field between them. So again, like I said, on Thursday, we will continue, and we will actually talk pseudo-quantitatively how the force between what the force on a moving charge is given some external magnetic field. So I'm going to end lecture there with that little introduction, and I will open it